Today we're going to learn how to do computer vision with Keras/Tensorflow, and we're going to work on a problem on MLPro classifying handwritten digit images. So in this problem, our goal is to develop a classifier that runs on a phone and can predict handwritten digits on the fly given the image frames recorded in real time. And we are going to work with the UCI handwritten digits dataset, which we can view here, handwritten digits dataset, and let's see, it is going to show up here somewhere, probably in the dataset description. Nope, not there. Sorry for... Oh, maybe here. Nope, not here. Handwritten digits on Google. Let's see if that works. Oh, here we go. Okay, so on Google Images, we see these pictures of handwritten digits, and our goal is to classify them. So if we get a picture of this handwritten 2, we should predict 2. If we get a picture of this handwritten 8, we should predict 8. So that's the goal. If we look at the data, as we know in computer vision and in general in computer science, images are represented as matrices of numbers, where each number in a position in the matrix is the value of the pixel in RGB, or in this case in grayscale, so just one color channel at that position in the image. So like this highlighted thing is one picture, this highlighted thing here is another picture, and etc. So that is our goal, is to predict one hand-encoded label representing the numbers 0 through 9 from these images. And we have two functions on MLPro that we can modify. The first is this ModifyX, where we can take this input representation for our images, which are 2D NumPy arrays, and return a different representation that we'll want to use to feed into our classifier. By default, we're reshaping the input image so that it's completely flattened. And that means we take each image and make it a one-dimensional vector. So like the vector would have these numbers and then these numbers right after it and then these numbers right after it, but not as different rows, basically just one giant vector. And the reason we do that is because in our create model function down here, by default we're given a dense neural network, a multi-layer perceptron, which takes in a bunch of nodes as the input, but those nodes are kind of lined out in a linear fashion because they're a vector. So each node represents a different position in the vector. So if we're going to be using a dense neural network, we're going to have to flatten it. So first let me move my face over here. And okay, so let's hit run code and see how this does just with the default implementation that's provided. And if we scroll to the bottom, okay, pretty bad accuracy at 9.71, precision at 0, recall at 0. Okay, let's try increasing the number of nodes in our first hidden dense layer and see how that improves things. Okay, better. Accuracy 38, precision 96, recall 28. Not bad, not good. Let's remind ourselves that because this is 10-way classification, random guessing would yield 10% accuracy, 10% precision, 10% recall. So we do better than random. So that's a good start. Let's try adding in another dense hidden layer, also with 200 nodes in it, and also with ReLU activation. It's these days the most popular nonlinear activation in neural networks. We have a invalid syntax error because I forgot to write a comma here. So put in the comma, hit run. Let's see what we get. And so on this one, we get, okay, accuracy 24, precision 24, recall 5. Okay, so adding a lot more dense nodes didn't really help things. Let's play around with the learning rate. Most important hyperparameter, can never emphasize that enough. And okay, so it was good that I didn't de-emphasize the importance of the hyperparameter, because look, by just using the same neural network architecture but having the learning rate go to 0.1, performance improved so much, 91% or 92% for everything. Let's just try a slightly even smaller learning rate, see what happens. If it's better, we'll go with it. If it's worse, we'll go back to 0.01. Even better, okay, 95, 96, 95. Right on, right on. Let's try an even smaller learning rate just to see what happens. And okay, it got worse, so let's go back to the 0.001. Let's also keep in mind that training a neural network is not, it's a stochastic process, so it's not deterministic, so it will be a little different each time. But it does appear that even though the 0.001 was a little lower this time, still tends to be about the highest learning rate. So okay, so that's good. But we've heard a lot that convolutional neural networks, CNNs, are supposed to be really good at images. So let's see if we could improve the performance even further with a CNN. So if we're gonna apply a CNN, we're going to have to do a couple things. First thing is, let's add in a 2D convolutional layer at the front, and let's look up com2d Keras on just to make sure we get the parameters right. So in the API, we see that the first argument is the number of filters. So let's say 64 filters. And the second argument is kernel size. Standard choice is 3 by 3. So let's go with that. And okay. We also need to specify the input shape in our first convolutional layer. So let's add that. And okay. But this input shape's not going to work, because if we're having a CNN, then it's going to take a square input if it's a black and white image. So let's go ahead and add xchange.shape of 2. So now it's taking as input a square image. And this is where it's important to come up to our ModifyX function to unflatten the representation, basically to have it be as it was. So we don't want to feed in a 1D vector as we were talking about at the beginning. We just want to feed in the original 2D NumPy representation. I'm just going to comment out that line in ModifyX because we don't need it anymore. Let's run this, see if we have any errors before we add to it. Oftentimes there can be a few bugs here and there when you're trying to switch around your neural network architecture. Input 0, is incompatible. Expected num dimensions 4, found num dimension equals 3. And then, okay, so what it's telling us is that the input shape that it received is not what it expected. So usually this com2d layer expects RGB images. So if it's not an RGB image, we need to tell it, okay, there's only one layer here. And if we're going to do that, we're actually going to have to reshape our xtrain to have that extra dimension of length 1. So dot reshape. And what that does is that instead of having a 2D representation of the image. It's a 3D representation of the image, but the third dimension is just of length 1 instead of length 3 like it would be in an RGB image. So syntax error. Did I type something wrong somewhere? Very possible that I did. Yes, I put the comma 1 in the wrong place. So great that MLPro has these syntax error warnings so that if I ever get something wrong, it can tell me that. Okay, so now it's saying the tuple index is out of range. That means that xtrain doesn't have a of shape of 2. So what I'm gonna do is I'm just gonna add a comma here, then add a comma 1, just to be super explicit that we're just gonna reshape it to be the same shape except have a 1 at the end. Okay, now we're getting a warning that these shapes are incompatible. The reason for that is that at the end of a convolutional layer, you're gonna have a 2D input, but then the input to the dense layer is 1D. So it's really important to flatten or add a flattening layer when we're transitioning from a convolutional layer into a dense layer in our neural network architecture. And okay, now it runs, but the accuracy, precision, and recall are all about the same. So let's try adding a few more convolutional layers and see what happens. So let's add another convolutional layer. Let's add some max pooling. Max pooling is a way to reduce the size of the input, and so let's look up max pooling 2D just to make sure that we have the right API format, and let's just add in this pool size argument. So pool size equals 2. Hit run. Let's see what we get. Takes a little while to train because as we add more layers, there's more parameters. Okay, so it's reasonably the same performance. We can add more convolutional layers, and we can maybe add dropout to add some regularization. Lots of ways we can play around with the neural network architecture here. It seems that because this okay, I added too many convolutional layers. Let me just remove that because eventually that output will be too small. Okay, so we're getting back to the 95s for everything, and we could keep on playing around with the number of filters, the filter size, where we add max pooling, how many convolutional layers we have, how many dense layers we have after it, the activation functions, the dropout rate, and the learning rate with respect to this new architecture, as well as the optimizer that we're using. It doesn't have to be Atom. So that's how you build a CNN in Keras TensorFlow. Hopefully it was educational to see me start with a dense multi-layer perceptron and change that into a convolutional layer, because in that process you got to see a lot of the common bugs that appear in TensorFlow development. So by me working through those, hopefully you won't spend a lot of time on those similar types of errors when you're developing models in Keras TensorFlow. So thank you for watching, and as a challenge, let's see if you can consistently build a model that will exceed 97% performance on accuracy, precision, and recall. So I will leave you with that challenge. Thanks for watching. Bye.